Hi, I'm Rishabh, and for my 15-112 term project, I've made a data visualization engine. So let's start. So as you can see, there are 5 modes. Let's go to the functions mode and the modular arithmetic submode. So for the sake of the demonstration, let's calculate x square mod 10 from 0 through 200. Degree is 2, maximum value 200, that's 0, 1, and 0. So I'm going to walk you through what the program does. Okay, so the first thing that you can see is whenever the function takes the value 0, the x value is printed over here and a notification sound is made. So in the normal function mode, these values will represent the integer solutions of the given function in the given range. Now let's see what this part does. So this part represents this data set in 3 different ways. First is a scatter plot, second is a gradient, and third is a network. So now if you look at it closely, the color scheme of the scatter plot and the gradient is the same, whereas that of the network is a bit different. Along with this, the width of the lines of the network and the gradient is different in order to bring out a distinction. So let's see how the color scheme works. Say we have to move from 9 to 4, right? That means turtle has to move from 9 to 4. So the color of the gradient in the scatter plot is going to be the color of 9, that means a shade of blue. And the color of the network is going to be a shade of green, which is the color of 4. So in other words, the gradient in the scatter plot take the color of the I minus 1th position, whereas the network takes the color of the ith position. Now this is important as we will see later on. So let's see what the scatter plot does. It is really important because it tells us how the function behaves over a long period of time. So right off the bat I can tell you x square mod 10 does not take the values 2, 3, 7, 8 as the scatter plot is non-existent. Along with seeing this part, since it's only shades of green and yellow, I can tell you that all preceding digits of 9 is only either a 6 or a 4. So now once the program is done, it allows me to take an automatic screenshot and save the file in whichever name I want to save it. So let's save it as text x2. Now I have to go to the directory in which I'm working in, and there you go, test x2. That's what we just made. So now let's see some other functions that this thing has made. Right? This is x to the same function with like a larger x value, x to the power 10, x to the power 7, x to the power 5, x cube, a complex modular arithmetic function, and this is x to the power 4 minus 69x cubed plus 1546x squared minus 12504x plus 29440. So now I want you to keep note of these 4 numbers over here. Let's go online to polynomial factorizer. So the same polynomial gets factorized to this. So this means this polynomial has integer solutions at 4, 10, 23, and 32. And that is what's represented here, 4, 10, 23, 32. So now let's change the mode. Let's go to pi mode. So the pi mode uses 2 different algorithms. One is the Chudnovsky algorithm, which allows me to calculate the nth digit of pi after the decimal point, and the second is the recursive algorithm, which is my own algorithm. So let's calculate the digits of pi, the first 300 digits of pi using Chudnovsky algorithm. So to save time, I've already done this for the first 1000 digits of pi using both the Chudnovsky algorithm as well as my algorithm. So my algorithm calculates the digits of pi up to the 6th point after the decimal point with accuracy. However, after that, it doesn't. However, what is interesting to note is that using both the algorithms, the number of zeros up till 1000 digits of pi is exactly the same. As you can see, this with the Chudnovsky algorithm ends here, and with my algorithm, it ends at the same point. Along with this, let's look at the distribution of the digits using the scatter plot. So over here, you look at this part, it's very similar to my algorithm over here, and the same can be applied down here. So what does this mean? This means that although my algorithm only calculates pi up till an accuracy of 10 power minus 6, the number of occurrences of each digit is freakishly similar, which is really cool. So now let's change the mode. So before that, so even if I close the background, this thing will keep on running and will allow me to take a screenshot whenever it's finished. So now let's change the mode. So let's go to quinary expansions. So this mode allows me to represent any base 10 number in any other base less than equal to 10. So let's pull up an example to check our answer. Let's put out a random number. Okay, it needs to be valid. Okay, So let's copy paste this. This is a base 10 to base 8 converter. So let's do that, base 8. And let's see what it draws. So again, if it encounters a 0, it puts the ith position of the 0 and allows me to take a screenshot. Okay, let's save this as test 8. Okay, so now let's go to the directory out of which we're working. There you go, test 8 is right here. And let's compare the answers. So this is what the online thing said, and let's see what we had. We had 3, 5, 0, 5, 1, 5, 0, 3, which is exactly the same. So it works. Now let's go to the last mode for the purposes of the demo, which is the scratchpad mode. So this mode is like my own notepad. I can draw equations, change colors, change multiple colors, go to eraser mode, draw whatever. I can also take a screenshot S and save the file as hi. And when I close this, you'll see that there you go, hi, with my workspace over here. So that brings us to the end of the video, but if you have more questions and if you want to know more about the source code, please feel free to go on my GitHub at Rishabh Chatterjee. Thank you.